Hello. Today, we would like to present some of the work we have been doing over the past several years about a particular unique branch of optimization called the scenario approach, which is a data-driven decision-making process with probabilistic guarantees. I'll start first from reviewing some of the key trends in the electricity sector, and I'm going to talk about some work that we've been doing to do risk-tunable real-time dispatch using the scenario approach. The major trends in the power systems can be viewed as an increasing level of decarbonization on the source side, increasing level of electrification on the demand side, and proliferation of digitization across the entire ecosystem. How do we design domain-tailored intelligence is needed at all scales to manage the increasing level of uncertainty in the smart grid. And in the context of optimization, operations research, in the area of scheduling, one can think of two big areas of focus. One is, how do you find the exact solution to a deterministic power flow problem or optimal power flow problem that is based upon the AC formulations? There's been tremendous progress along this line, and they are based upon a more realistic model, which is AC model, but solving them in a deterministic fashion. The other big area is to think of how to make a decision with a lot of uncertainties. And most of this work is based upon a simplified DC OPF model, but they are much more focusing on the optimization under uncertainties. Today is focusing on the second big area. In terms of making decisions with uncertainty in the power systems, it spans all the way from multiple months to days ahead until closer to the real-time operations. And as you get closer to the real-time, the level of uncertainty is shrinking, but also the decision that you have in terms of the time is also shrinking. And the approach that we introduced in this talk is applicable to these several different time steps of the decision-making process. So from a practitioner's perspective, several of the desirable features of helping the transition towards a decision-making with uncertainties includes, first and foremost, reliability. So we need to make sure that whatever decision we are making, there is a specifiable level of risks. And the second one is a lot of the data coming from the demand side or coming from the renewable resources do not have a well-defined uncertainty distribution. So it is desirable to have a framework that do not necessarily rely on a particular type of underlying probability distribution. And we have lots of data from the history, so we can utilize this as much as we can. And also, ideally, you should make it compatible with pricing and market construct. And this is quite fitting in this general framework called the scenario approach. It is very intuitive. You collect data from the historical samples, yet it is very rigorous in the sense that one can prove a posterior risk guarantee based upon the number of samples that is drawn from the historical data. And one can understand this uncertainty via the scenarios, and they could come from historical data or come from sample from distribution. And it is computationally tractable and it's probabilistically guarantees the posterior performances. We have been doing quite a lot of work along these lines in the context of power systems. But before we talk about those, let's first briefly review this problem. So one can formulate the problem as following. You're trying to minimize objective function with certain inequality constraints, but one of the parameters is subject to the uncertainty. So depending on the realization of these uncertain parameters, the optimization may or may not violate any of the constraints specified in a function F. And the red area region is specifying the region where a particular realization of the parameters might end up violating the inequality constraints. And that is the risk that we are defining in this particular context. And the violation probability can be then quantified by this particular probability measure. And there is a very important concept called support constraint that is associated with this approach. A constraint is considered as a support constraint is the one that will improve the solution of the final outcome if this constraint were to be removed. In other words, it is a binding one that if this were to be removed, then the overall problem is going to be ended up being in a better optimization solution. And the number of support constraints is essentially defining the complexity of this solution. It is shown through the pioneering work by Professor Kempe and his group that the risk that was defined in the previous couple of slides has a beta distribution. And this is the key original result that specifies the size of the sample as a function of the level of the risk and the confidence interval, as well as the D, which is the decision variable or the complexity that is defined by the support constraint. So by establishing this very important relation, one can directly thought of the size of the sample as a way of tuning the posterior risk that a practitioner would desire to have. So we first apply this in a look-ahead dispatch problem of power systems, where you can have the total cost as minimizing the total generation cost with the power balance and generation adequacy constraint, as well as the branch flow and ramping constraints. So we studied this in a large 2000 node system. In the original vanilla version of the scenario approach, given the size of such a problem, it is quite computationally expensive to coming up with any meaningful level of risk and associated number of samples. It requires more than 1 million scenarios in order to bound the performance of the risk to be less than 0.001. However, one thing that we have observed is that even though it requires a significant amount of sampling sizes, the actual realized violation probability is actually much less than the theoretical limit. So that triggers further thought by utilizing the more recent work done by Professor Kempe's group called Weight and Judge. We were able to further tune down the size of the sample by having an important insight, which is the original result of the theory was for a fully supported problem. However, in many of the large-scale network problems, a problem is not always fully supported. In fact, their maximum number of active constraints could be significantly less than the number of total constraints in the original setup. We leverage this insight and identified that the power system operation is far away from a fully supported condition. By utilizing this insight that only a very small fraction of the lines are actually constrained at the same time in this context, most of these lines are not congested. Only less than 3% of the lines are congested at the same time. By utilizing this insight, we were able to update a new version of the scenario approach in which a reasonable risk level, in this context, less than 0.005, only require less than 870 scenarios. And that makes such a problem and such approach very scalable for real-world power systems. To summarize, we showed you a particular use case of a scenario-based approach to solving the real-time dispatch. It guarantees the loss of load probability. It is very scalable in large-scale power network. And there are many more activities, including a recent work that we have published about non-convex setting of utilizing the scenario approach. And with that, I'd like to stop this and leave you with this particular slide that summarizes where the scenario approach is fitting in the broader scheme of things of understanding the issue of uncertainty in the optimization problems. Thank you for your interest.